Let me show you something right quick before we get to the main stuff. Your question about when the quiz will be graded, it's got to be soon. I just finished the 305s in the nick of time, so hopefully Thursday. What's it been, 3 weeks? 4 weeks? Been a while. If you go to my website, Lowery, LOWERY.tamu.edu, and go to 345, I probably need to move these inside to the syllabus. There are some nifty things. This is where you click to get to the syllabus. There are things called volume integrals. Here's a copy of them, so we can tinker with them today. She is not going to give you her telephone number. You already have it? Pass those around if you already have one. If you don't, go ahead and take one. They're out on the web. Once you lose that one, which you will, and that's okay. They are called volume integrals. They have various and sundry names. I think our book calls them, I don't remember what. But basically they are for calculating volumes. There's a second sheet of them. Got more of them. It's probably overkill. You probably don't really need that many, but they're there. There is an information sheet on using virtual work. I think it pretty well summarizes how to solve for the forces in deflected structures. For trusses, if you are busy talking to your buddy and not listening to me, then you might need this because you probably didn't get this information previously. Using volume integrals. This is an example of using those volume integrals. We'll try and do one of those today. So, just where you can get some more information on stuff we've been doing and stuff we're going to do today. All right. Now, I stole some of the equations out of the book just to kind of summarize them. I've learned my lesson. Don't copy them out of the book and write them down because I get half the terms wrong thinking about something else. Equation 913, we related how a beam bends to how much moment you applied. I believe the original equation said d theta dx is equal to m over ei, was curvature. Equation 1020 in your text, we worked out how much work is done by one or more loads, dummy loads, unit loads, virtual loads, traveling through displacements on a structure that got displaced due to some real loads. For example, if you came out here on a structure and you put a unit load on there, it doesn't have to be unit, it can be any number and it'll cancel out. Then it'll bend the beam down slightly. You see that? And then if you put a real load on the structure, it will bend the beam some more, and that unit load travels through this deflection at this point and causes some work. And that 1 times that displacement, that 1 times this displacement work is stored in the beam due to energy, due to the due to the work done on the beam. It's strain energy if it's bent. If it's a truss, then it is deflection. If you bend something, we've already done the stuff for axial loads in bars. If you bend something, the little bit amount of energy that you store due to a unit load is the moment caused by that load times how much theta it caused. The total amount of it, you'll have to usually integrate it. Unlike trusses where the load is constant throughout the member, this number usually changes as you move around on the beam, so you'll have to integrate the term. And the book doesn't have a sum, but the truth is in most cases you'll have more than one beam involved, so you'll have to sum up all of the individual I is equal to 1, 2, 3, 4, 5, however many members you have in the structure, times m sub q due to the q loads times d theta sub I. So for deflections, we set how much work you did on it to how much strain energy got stored in the structure. The sum of the q, this is due to a force, times the deflection due to the real loads. And this will be a particular deflection because the terms that you will put in here, you'll put a unit load on here at a point of my interest and only one at a time. And the direction that you put the load is the direction you will get the answer. So if you want a horizontal deflection, you'll be putting a horizontal unit load on the structure at that point. If you want the vertical displacement, you'll be putting a vertical load at that point. If you want to know the deflection of that point at a 30-degree angle, then you put your unit load on there at a 30-degree angle, and when you get an answer, it would tell you the displacement of this point to some new location in that direction. And if the answer came out minus, then that means that the point didn't move in the direction you put the unit load, it went the other way. Setting that work done to that energy stored, substituting m sub q, you get, d theta, you get m sub p dx over ei times m sub q. And basically this is what we're asking you to do. First, on this side you probably only have one force, and it's probably a 1. And it'll be multiplied times the deflection due to the real loads, which is usually what you're looking for. It'll be your job to give me moment diagrams due to the unit loads, what we call the Q system. And it'll be your job to redraw the structures and give me equations due to the P loads, the real loads, and then dx over ei, and integrate them along their length and add up however many members are in your particular structure. The energy stored or the work done on here, if you instead put a moment, then I can multiply the magnitude of the unit moment, force, unit, times the rotation that that unit moment rotated through in the real world due to the real loads, theta p, and set it equal to this the same term. The only difference now is m sub q would be due to a moment applied to the structure as opposed to a real linear load applied to the structure. So let's try an example. I've got a structure, got a load on the end of it, P, it's got a length L, and I would like to know the deflection. Let me put some real numbers in here just so we can use some numbers. 10 feet, 6 kips. The structure has the properties E for the material of choice, say steel, has a moment of inertia for a W12 by 40 wide flange, whatever it is, so many feet to the fourth. You're going to have to either change this to inches, you're going to have to change this guy to feet. Probably most people go ahead and put in a 12 inches per foot before we get started. Make that length 120 inches. And the rule says, find me a moment diagram due to a unit load. So I say, all right, I'm going to put a unit load on that structure at the point where the boss wants the deflection, and in the direction he wants to know the answer. And sadly, he hasn't told me that, so I'm going to have to go talk with him. Where do you want the answer? He says, well, I wanted the answer in the middle of the beam. I say, I can do that. 10 times 12 is 120 inches. So that'll be 60 inches to the place where you want the answer, and another 60 inches to where the load is applied. You need 2 moment diagrams. You need one due to the unit load and one due to the real load. So you redraw the structure, and you draw the structure with a unit load applied. And you generate a moment diagram for that case. Generally speaking, I would solve for the reactions. Knowing the reactions, I would then draw a shear and a moment diagram. That's in the case where things are really ugly. Here's a simple case like this. Shouldn't be a lot of trouble to it. I'm going to say plot on compression side for no reason other than this is the compressive side and there's nothing down there. So I'll plot all moment diagrams on the compression side for this problem. The moment here is 0. The moment here is 1 times 1 inch, 1 times 2 inches, 1 times 8 inches, 1 times 40 inches, 1 times 60 inches. The magnitude of the moment is 1 times 60. 60-inch kips. His name is M sub Q. A lot of books call him Little M. I kind of like that better, but this is a great book, so it's not worth throwing away the book. But a lot of books say that the answer is equal to the integral of m dx over EI. Kind of like that, because little m sure sounds like little loads, and big M sounds like real loads. M sub Q, okay. Next, I'm going to draw the beam redone. And I'm going to put the 6-kip load out on the end. And this will be M due to the real loads. And the moment diagram looks like that. It's 120 inches. 6 times 12, 720 inch kips. Drawn on the compression side. It's critical that once you pick a side for any one of the members that you match up the side you draw for this and the side you draw for this one. In other words, if this is on the compressive side and you draw it on the compressive side, then you got to do the same thing for this one. By the same token, if you have different ranges of integration, then you're going to have to start at the same point. In other words, you can't start here. Let me say you can't start on this end and go that way if it's easy, and then start on that end and go that way because it's easy. Whatever you pick in region 1 for your starting point has to be the same. And whatever you pick for your x equals 0 in region 2, got to be the same for both of them. You can't go this way on one of them and that way on the other. You can pick anything you like, but it has to agree. So it's my job to say that the sum of all of the Q loads, which will be 1 multiplied times the deflection due to the real loads at the point of application of the unit load in the direction that you decided to put the unit load, is equal to integral of m sub q m sub p dx over ei. In this case, we only have one of them, one member, so the summation doesn't really apply. And this will be throughout the member. So now I need these equations. I'm going to pick this as x in region 2. I'm going to pick this as x in region 1. Take your choice. You can start from this end and say 60 minus the slope times the distance. It won't change a thing. So here is m sub q. This is in region 1. This is in region 2. M sub q is equal to, due to the Q loads, there is no moment. And due to the real loads, 6 times x. And I don't know, it's up to you. You might really say it's a minus 6x, and probably ought to if it's a negative moment in that region. Whoops. Excuse me. In region 1. Now I'm going to do region 2. In region 2, m sub q is equal to x, 1 times the distance, and for m sub p, got to start here. The starting value is 6 times 60, and it increases as you go. So it ought to be a minus 360 minus 6 times x. It's equation of a straight line. Check the boundaries. M sub p is equal to minus 6x when x is equal to 60. You should have 360. That's okay. When x is equal to 60, you should have minus 360 minus another 360. That's minus 720. If it fits those end conditions, you're probably okay.
Shouldn't m sub q be 0?
Thank you. In region 2, I'm so used to just, all right, this is this guy, right? My 1 and 2 are backwards, thank you. I started off in region 2 and I start off in region 1. So yes, you're probably right. The equations are reversed. Started off in region 2, m sub q is 0 and m sub p is, this is good. Get over to region 1, m sub q is x, and m sub q starts at 360 and builds up. Now here's your job right there to integrate those equations. It says that 1 is equal to the integral. First off, we'll go in region 2 from 0 to 60 of m sub q. All right, well, that tells me something. Times a minus 6x tells me that if either the real moment or the moment due to the unit load are 0, there'll be no contribution of deflection in that region. Times dx over EI. EI, if it's constant, can go outside the integral. Plus, this is for region 2. This is for region 1. The integral from 0 to 60 of m sub.
Should the limits be from 60 to 20?
Yes, if you held x at this point. In other words, when I decided to pick up ship and move over here and start integrating from here to here, from 0 to 60, then my equations changed. Now, if you say, well, what I had planned to do is I planned to stay here the whole time and integrate from 0 to 60 and then just let this new equation come on stream and go from 60 to 120, that'll work just fine. It'll also work if you decide to pick this end and go to the right. You'll get exactly the same answer. So m sub q is x. Is it a minus x? Keep my signs straight here. It's below the line, minus x, times a minus 360 minus 6x dx over EI. Phooey. This is 1 times, this is your sum of the q, times the deflection at the point of interest. In your case, it is 1 times the deflection at B. So you get that the deflection at B is equal to 1 over EI times the integral of 360x minus times minus plus 6x squared is equal to 1 over EI times 360x squared over 2 plus 6x cubed over 3 from 0 to 60. And then you plug in 60, whatever you get. 1 over EI times 360 over 2 is 180, is 160. Well, no, that's right, 180. 180 times 60 squared plus 2 times 60 cubed tells you what your deflection is. Now then, sometimes if a little simple one like that gets that ugly, they can get really nasty. This isn't hard. Getting the equations isn't hard. And then integrating isn't always hard, but you can imagine that if you start getting parabolas and all kinds of other things and a bunch of ranges, it can get relatively ugly. So what somebody noticed was that integrating the height of something times the height of something dx is actually nothing more than the volume of what's inside there. As an example, pretend that that hasn't been used. If you have something that looks like a rectangle when you do it on one side and looks like a rectangle on when you look at it from the side, and you were to integrate that height multiplied times that height multiplied times dx from end to end, you wouldn't get anything except the volume. For example, here's an eraser that I had, which was square like that one, and which I cut it diagonally. Looking at it from one side, you see a triangle. Looking at it from the other side, you see a rectangle. So it looks like so. If you'd like to know the volume inside of that triangle, all you have to do is multiply this height times this height times dx over EI. Multiplying that height, m sub q, times that height, m sub p, times dx, and do that all the way from one end to the other end, and you have the volume of this eraser. And people have been calculating volumes of things forever. And so somebody who was trying to integrate the height of something times the height of something times dx from 0 to L said, you know, I know a bunch of people who do this all the time. And I said, okay, who are they? He said, they calculate volumes of erasers and volumes of all kinds of things. He says, for example, here's somebody who had an eraser, and they cut it diagonally, and then they cut it this way, diagonally, and it's got a volume. And he says, here's how you find it. You simply multiply the height of this triangle at any time times the corresponding height of that triangle at any time and integrate from one end to the other, and you get the volume of the shape. So I said, all right, where do they have these things summarized? He says, well, they're called volume integrals, and they got various and sundry other names for them. Here we go. He says you got to be careful when you use them because there are several terms involved. But as an example, the volume of a eraser turned up on its edge and then laid down flat is equal to the integral of this equation times the integral of, times that equation times dx over, there's no e over EI in the volume. He says in the volume of such an eraser is the height on one dimension times the height of the other dimension times its length. There's the height of the first one, there's C, and there's L. If you cut the eraser in half, he says, as you might imagine, the volume is LAC over 2. Or if you cut it the other way, it's LAC over 2. He says if you have an eraser and you cut it, you don't cut it all the way down to 0, but rather you cut it ½ inch down and ¼ inch down so that you have a trapezoid. But when you turn it up on its edge, it still looks like a rectangle. The volume underneath that, in other words, the integral of dx across the length is the length times the height of this dimension times the average height, and I say that's sounding familiar, the average height cut in half. And they can get really ugly, like parabolic spandrels combined with triangles. It's got more terms in it, but it's the same idea. So let's try it on ours, the one we just tried. You have those. Can't have gone far. There it is. You and I are trying to integrate an eraser that looks like a triangle when seen from the side and was drawn on the thinnest piece of paper on earth. The volume of such an item is equal to nothing. And then we need the volume of an eraser that cut on one side looks like a trapezoid, and when you roll it up 90 degrees and look at it on the edge, it looks like a triangle. Here's the answer for such an item. Fat triangle on the left, that looks good. Combined with a trapezoid, that looks good right there. And it turns out that it doesn't seem to matter whether A is bigger than B or vice versa. Let's check that out. Here's one where the thing is turned around the other way. And, gee, that don't look right. Yeah, that's okay. 2A, 2B, B, A, that's okay. Incidentally, I think there's one in your book that's wrong. That one's wrong. Got a 2 in there, should be a 1. At least in my book. I don't know how old my book is. What does yours show? Does your show still show a 2? Can't imagine they haven't driven that out of those books yet. So you need to change that in the back of your book. All right. So what I'm looking for now is I'm looking for the integral of this times this, dx over ei. I'm looking for this to be combined with this. And I'm going to mark the numbers down carefully because that's where most of the mistakes come from. This one is 60. This one is 720. This one is 360. And the length is 60. And according to this guy, the integral of m dx, you got to do your own EI, volumes don't know EI, is equal to the length times C times 2 times A plus B divided by 6. This number is labeled as C. This number is labeled as A, and this number is labeled as B. You'd be surprised how easy it is to get these numbers jumbled up. So it's equal to, the length is 60 times 60 times 2 times 720 plus 360 divided by 6. See a mistake? Tell me now before it gets out of hand. Who worked that out just because they were bored? Nobody was bored? I don't believe that. All right. Straub?
Yeah.
Why do I have your name circled?
Got bored and now you're asking.
Is that what it was? All right. Straub, what is 180 times 60 squared plus 2 times 60 cubed?
It is 1.08 times 10 to the 6.
Thank you. Times 10 to the 6. Sure sounds like a lot of deflection. Not necessarily a problem because we're going to divide by 30 times 10 to the 6th, 30 times 10 to the 3rd, KSI, and the moment of inertia, whatever it is. So that divided by EI. And if you guys usually always pick up my mistakes, so this ought to turn out to be the same. It does? That's nice. I like it when it works. 1.08 times 10 to the 6th divided by EI. Okay? And sometimes these things are just wonderful. I mean, they really can save you a lot of time and a lot of effort. All right. I've got a frame. This dimension right here is 300 inches. This dimension is 200 inches. I'll tell you just between you and me that there is a pin at that point and a fixed end at the bottom. And that there is a load on the structure of 2 kips per foot, which is equal to 2 kips per foot times 12 inches inside of a foot, because I got a feeling the boss is going to give me EI in inches, so I'm going to go ahead and get it fixed now before I go any further, is equal to 1/6 of a kip per foot. Per inch, thank you. Foot cancels foot, inches. Now, we'll get into how to solve the problem, but I'll tell you now, there shouldn't be any deflection here, but I can't solve for the forces inside of that structure as it now stands, because it is statically indeterminate. There's an unknown reaction in this direction, a possibility of an unknown horizontal reaction, and a possibility of an unknown moment, and an unknown reaction, and an unknown reaction. There are 5 forces acting on the exterior surfaces of this, and I was only gifted with 3 equations of statics. In fact, that's all I gave you. And so we are 2 degrees statically indeterminate. And so what I'm going to do now is just jump ahead and tell you that what we will be doing is you will be taking some of those sad reactions off of there, those things we can't find, and letting the structure deflect however it wants to, even though you don't like those deflections. And you will solve for those deflections you don't like, and then we will come up with ways to make them go away and get the original structure back. Here is the real structure. Now, I don't know if I should have even mentioned that. That's where this really came from. This is 200 inches across here, and this is 300 inches tall, and this is 1/6 of a kip per inch of loading on the structure. That is your real load system. As you know, in order to get the deflection, you're going to have to integrate all of these members, M, due to the unit load that you decide to put on the structure at a place you decide where to put it, in a direction you decide which way it ought to go, times the real. Thank you. Oh. Thank you. Times dx over EI. Incidentally, I need to go confer with the boss about these members. I asked him, are these all the same? And he says, well, no, this is a column, and it's got 2 EI, and this one has EI. I say, well, I do need to know that. That's going to change the answers. Therefore, it's up to you to go get a unit load on this thing and find the moment diagrams involved and put the real loads on this thing and find the moment diagrams involved and integrate them dx over EI, where EI doesn't mean EI. EI means whatever your EI is. So here is real loads. And here's the moment diagram that goes with the real loads. That moment diagram starts out at 0. For no reason other than the heck of it, I'm going to draw it on the tension side this time. Drawn on the tension side when we get to the moment diagram. This will be 0 in the middle of the beam. The moment will be 1/6 tall times 100 wide times the distance from the centroid of the load past that point, 50. So the moment's going to be on the tension side. I need to know the following number. Got a calculator? Got a calculator? Oh, you do? All right. Would you please multiply 100 divided by 6 times 50. 833 would be plenty close. We probably know those other threes are hanging out there. And now then I'll cut the beam at that point. Give me the following number. 200 divided by 6 times 100. 3333. Thank you. Inch kips. Turns out it's a parabola. If you would like the equation for that line so that you can integrate it, then M sub P, I'll come down here and I'll show you the beam, and I'll show you it's been cut. It, of course, extends on down the road. Here is the load. That is 1/6 of a kip per inch. This is arbitrarily picked as X. Incidentally, the next time you do business on this guy, you don't have a choice for X. Somebody's picked X. You're stuck with it now from now on. This is where it's been cut at X. There is a bending moment on the beam. I highly suggest you always put the unknown moment in the positive direction on the beam. I don't know exactly what to tell you once we turn this thing this way to get this beam, but it probably makes sense to show the moment in the positive direction, and if the moment equation comes out minus, then you just say it's a minus. Here's the moment due to the real loads. Some of the moments about that point, some of the moments about the cut face is equal to 0 is equal to minus M sub P minus, the load is 1/6, the height is the base is X. Question? Don't let me make a mistake, for heaven's sakes. Okay, times X over 2. And so M sub P is equal to minus X squared over, is that right? minus x squared over 12. Let me check. 1/6 is the height, x is the base. The centroidal distance is x over 2, 2 in squared. So minus x squared over 12. Now then, I'm going to show you the moment diagram on the vertical piece. When you turn around a corner like this, the moment's the same on both sides of the corner. Doesn't matter if you want to, you can come on down inside of here and cut. You see you get the same moment in the corner as you did on the other side of the corner. And so it's 33, 33. And the force is 1/6 times 200 multiplied times the moment arm is the same all the way down. And so the moment stays the same all the way down. There's your moment diagrams, and there's your moment equations. Let's call this guy here region 1. Let's call this guy here region 2. As a summary, the moment due to the real loads in region 1 are equal to minus x squared over 6, and the moments due to the real loads in region 2 is equal to 33, 33. And I don't know what you want to call that. Positive, negative, it's up to you. We called this guy, this moment here, we called him a minus in the equations. So I'm going to list him as a minus, and I'm going to list him as a minus. And I guess I'll list him as a minus. But whatever you do, I don't care what you do. You can call him minus, you can call him plus. But whatever you do, you got to do the same thing when you put the unit load on there. Yes, sir.
I have a question. For the moments and the real loads in 1,
Right.
that's negative x squared over 6. Why isn't that over 12?
I'm sorry, I don't understand the question. Thank you. Because I'm thinking what I'm going to do next, and I grab numbers and I slap them on there, and I let you tell me, hey, dunce. And then I mark your name like I did Stroud for some reason. I don't even remember why I marked Stroud. I don't even remember why I did that anymore.
You said something about failing.
Yeah, now I remember. Thank you. Okay. Let's see. Real friend here. Yeah. All right. So we've got equations for these guys. Again, you may well ask, you do this for a living? Yeah. You spend all this time? Yeah. They pay you by the hour. It's good stuff. And once you understand how it all works, then you're not really a danger to society if you go get a computer program to do it for you. Incidentally, I forgot to mention, it's too late now, but on that same page where I showed you where the volume integrals were, where they were located, there is a computer program out there that'll do it for you. It's an Excel program, and it's got these little pictures on the top and these little pictures on the top and different pictures, and they got the pictures on the side. And over here they say, tell me what is L and what is A and what is C and what is D. You just tell him all the numbers. You put the numbers in there, and right here he'll tell you what that turns out. That integrated with that, and it shows up in the box. So kind of handy for homework. Obviously you have to still be able to use these volume integrals on an exam, or you have to be able to do the integral work, one of the two. Most certainly it'll be provided, unless I want to see if you really can do this, but I don't hate you yet. So probably it would give you the volume integrals, yes. I mean, this is really something this is not 345. This is something you've already learned, and I could care less about examining you over it. Now then, we have pictures of moment diagrams and we have equations for moment diagrams in these regions. If you'd rather use volume integrals, you can. If you'd rather do the integral, you can. The next thing I need to do is I need a picture with the unit loads on it. Now there are two of these things that I need. Because this thing is unfortunately restrained in two directions, no vertical deflection is permitted. I'm going to be looking for this unfortunate downward deflection, or deflection, I don't know which way. I guess I do. And I'm going to be looking for the horizontal deflection. So I'm going to need a unit load in the vertical direction to get the vertical deflection of the real structure when you didn't support it like you should have. And I'm going to need another one that shows a horizontal deflection applied at that point. Why at that point? Because that's where the deflections are supposed to be zero, and for your idea of life, it's not zero. So here's unit loads for, let's just call it delta. This is point A, B, C, the delta at C vertical. To get the vertical displacement, you'll have to come to the point you want to know where what the deflection is, and you'll have to put a unit load on it, and it'll have to be in the direction you think the answer goes. And it doesn't matter. If you think the real structure deflects up at that point, put it up. And if you're wrong, the answer will come out with a minus sign on it. And it'll come out with a minus sign. That'd be a minus sign. That's not a plus, but it's a minus. Wheeler, what's the sign? Got it wrong! That's okay. That's all right. But you always know you got a 50-50 chance, don't you? What's amazing is somehow in his mind there's a little short tape, and he can remember about the last 3 seconds of what I've said. All right. Here's the moment diagram if you would like a picture of it. Looks like this. Messing with Sasquatch. The moment diagram is 0 here. 1 times 1, 1 times 2, 1 times 8, 1 times 40, 1 times 200, and therefore the moment diagram looks like that. And that value reaches 200 kip inches. And when you turn the corner, if you'd like to see a free body of that, looks like that. There's a 1. This is 200 inches. And therefore the moment at this point will cause tension on the left-hand side, and the value of the moment is 1 times 200. And if you cut it a little longer, it's 1 times 200, and so it's constant. So your moment diagram looks like so. And these are your, what do I call that M sub Q for heaven's sakes? Oh, it's not, it's P. Just an ugly P. It looks like a Q. Due to the real loads. All right. Now then, I can write an equation for that without drawing any free bodies. This one might have needed a free body to make sure I get the equation right. The moment due to the Q loads in region 1 is equal to X. 0 times 1, 1 times 1, 2 times 1, 200 times 1 is just X. And the region 2 has a load equal to 200. Now let's look for our signs. This pushed down, causing tension on the top, and I drew it on the tension side arbitrarily. It's nicer than drawing it on the compression side where they kind of run into each other. And that tension on the top stayed tension on the left of the joint. And so this is the tension side. By the same token, I lucked out, I wasn't even thinking about it. This pushes down, causes tension on the top, compression on the bottom, drawn on the tension side. You have no choice. Got to be plotted on the tension side because that's what you did for this guy. And the tension is linear, and then the tension's on the left-hand side. It stays on the outside fiber. And therefore, this should say minus x, because you call that negative. And this one should say minus 200. Now that I'm ready to find the deflection at C in the vertical direction. The deflection at C in the vertical direction is equal to the integral in region 1 of the equation m sub p times the m sub q. That's reversed from what we have in the book. This one is the m sub q, and this one is the m sub p, times dx over, and I'm going to now divide by our real EI. According to the boss, our EI for this piece is really EI. So I'm going to change EI generic to EI for our beam. And that should be integrated. It should start at x equals 0, and it ought to end up at 200. Plus the integral in region 2. In region 2, the real moment is minus 3333. And the moment is minus 200. And that's times dx over a generic EI. When I talked to the boss, he told me that the column had 2 times the moment of inertia, or it's made out of a material that's twice as stiff as steel or something, but the EI there is a 2EI. So I divide by 2EI. And that gets integrated from x equals 0 to the end, 300. And that's equal to the integral of x cubed turns out to be a positive. Good morning.
Good morning.
How you doing?
Good.
Great.
Well rested.
You're all rested? Well, you should be. You slept an extra hour. All right. The integral of x cubed is x to the 4th over 4. So that's x to the 4th divided by 4. Already divided by 12. Already divided by EI. Supposed to be evaluated between 0 and 200. Plus, minus times minus, this guy will also be an added deflection. Something times one integral up is x, and that piece is supposed to be from 0 to 300 divided by 2, and we still need an EI. Equals to Got a calculator? You don't have a calculator? You come to an engineering class without a calculator? I'm glad you remembered your shirt. Got a calculator? Don't have a calculator, a little pocket of poverty there. Nobody got a calculator. Gitman? didn't even wait. You're it, man. You're the only person who brought a calculator today. 200 to the fourth, divided by 4, divided by 12. To that, add 3333 times 200 times 300 divided by 2. While you're doing it, I'll ask somebody else for the answer. 3.37 times what? To the seventh, okay, times 10 to the seventh. Now, if that's not right, that's your problem. Well, I don't care if it's right. I got a number here, and I'm moving on with my life, divided by EI. And when you get home and that's not the right number, that's because you didn't bring a calculator today. But you know how to get the answer. Now then, by volume integrals. The nicest thing about volume integrals is you don't have to write the equations in those regions. All the volume integrals ask you is end values, or perhaps in the case of a parabola, he wants the end value, he wants the midpoint value, and he wants the end value. And these can be plus or minus. It doesn't make any difference. Anything works. That's why you see it's got a couple of shaded things where C is the left end, and on the solid shaded triangle it's that high, and the one behind it it's that high. It's trying to indicate, make any difference what C is. Plus or minus of any magnitude. It doesn't matter if you got the big end on the right or a big end on the left or anything else. These triangles, it matters. If you've got a triangle facing the same way as a triangle, you get one answer. But if you got a triangle facing the other way with a triangle, you get a different answer. Those, it's important that you match up the one end with the other end. Some of them, for example, when you combine two triangles like this, you can call either of the triangles A, and you can call either of the triangles C. But when you pick your two triangles, L3 has to be shorter than L1. So in other words, if this number right here is 8 feet, and this piece right here is 20 feet, and this piece right here is 4 feet, and this piece right here is, well, it has to be had up to 28, so that'd have to be 24, because they both have to have the same length, then this won't work, because you picked the wrong ones. L3 has to be shorter than L1, and you picked them wrong. So you'll have to reverse these numbers. You'll have to bring the 4 down here, and the 24 down here, and the 8 up here, and the 20 up there. So you got to follow the rules that the guy did when he did the integration. So by volume integrals, I keep losing things. Not unusual. There it is. By volume integrals, you need to add this with this, and you need to further add this with this. And then when you get this one, you're going to have to divide it by 2 because don't forget your EIs. This piece here has got an EI, and this guy's got a 2EI. It's equal to the volume integral for a parabola. Looks like this. Sorry, I don't have one where the big end of the triangle's on the left. You're going to have to be smart enough to figure it out. Where this is 3333, a negative, and this is 200. And the big end of the parabola got to match up with the big end of the triangle, so that's this one here, where the big end of the triangle is 200 minus 200, and the L again is 200. Here's the term you're looking for right there. Golly, that's sure easier than writing all those moment equations. Now, wouldn't steer you wrong. It's real easy to come up with a case where it's not on this page. All I'd have to do, or all anybody would have to do, for example, would be to put this load on a beam. A triangular load on the beam. That would give you not a parabola. It's 1 degree higher, be a cubic for the moment diagram. In which case you're stuck. You just got to use the integrals. So LAC over 12, the L is 200. Let me write down what I got here. That's an LAC over 12 plus, these I already know what that is. That's LAC. That's just an eraser. Turn. That's right. In the long run, then that will be divided by 2. Now let me put the EI in here. I want to make sure you see that this 2EI here is because of the EI. It's not because of the LAC, the volume. So it's equal to, the length is 200. A is, well, I don't know which one's A, doesn't matter, they're both multiplied together. So minus 3333 times a minus 200 divided by 12 EI added to 200 times A minus 3333 times a minus 200 divided by 2EI. And thank you. We got a 3333 and a 200. One of these here. Thank you. The length was 300. Thank you. It says L. There's a good way to get in trouble. Well, they all say L. Well, so I just put 200 everywhere. And not going to work. Got to be individualized for that member, including his length personally and his length EI personally. Length. Thank you. So no question about it, those are really nice for solving for these things. All right. Here is the structure. That's point C. I'm now trying to solve for the horizontal deflection. Booth? How do I solve for the horizontal deflection? I have solved for the vertical, delta at C vertical, delta C vertical. What do I change to solve for the vertical deflection? That's all you do. You change your 1 to the horizontal direction as opposed to the vertical. Thank you. I'm looking for, I've got the vertical. I'm looking for the horizontal. To solve for delta C horizontal, I put the unit load at C and I put it in the horizontal direction. All right. Garza? Garza's not here today, huh? Morrison, you get lonely there a lot? No. No, they there every now and then? Okay. I remember they were there during the quiz. I didn't recognize them really. Wheeler? Oh, Wheeler's awake. Look at that. Wheeler's got blue eyes. I don't think I've seen him this semester. Well, I lie a lot. Wheeler, what is the moment in this member right here due to this load right here? That's right. That's very good. I told you you could do this stuff in your sleep. Lane, what is the moment in this vertical member as we move down due to this load? Well, how big is it here?
0.
How big is it 1 inch down?
Still 0.
Well, not 1 times 1 is 0. I mean, if it is, then loan me $1. Okay, and what is it 300 inches down?
300.
That's correct. So in other words, it just builds up linearly and drawn on the tension side. It looks like this. And this would be a minus 300 because we decided that things drawn on the tension side, we call them minus for no reason. And I could write the equation for M due to the Q load in region 1 is equal to 0. And M due to the Q load in region 2 is equal to minus X. Just keeps on building up. But I tell you what, I just as soon go ahead and do volume integrals. The deflection at C in the horizontal direction is equal to one of these combined with one of these. We get to use our old M sub P diagrams plus one of these combined with one of these. $33.33. Marino, what is this answer right here? It is indeed. Integral of that dx over I is 0. Baker, what is the volume integral for this condition? Got your volume integrals with you? Okay. Go find a triangle. You know, they may be facing that way, which is fine. They won't change the answer. It'll just rotate it 90 degrees. It is LAC over 2. That's correct. And this length is 300 inches long. And therefore it is delta at C horizontal is equal to 0 plus LAC over 2. And then, of course, it's divided by EI. And this is the guy who's got the big EI, so we'll have to divide by 2EI. Now, the length is 300. A is that right? Yeah, well, it came from this one here. There's a minus 300. I'm trying to finish before the time here because I can tell this guy's ready to go. And he's zippering like crazy. Times a minus 3333. There's LAC divided by 4EI. Just that easy. All right. See you next time.
Thursday's homework, just because I'm not sure if I'll be here or not.
Yeah, sure.
Put in the same stack.
That's fine.